And now on to the session today. It's our fourth session of the conference. And like I said, we'll be covering calcined clays. How are they made? Who is making them? And why are they a game changer for our industry? Well, we have all the experts here to answer all those questions. I'm delighted to be able to introduce Luis Felipe de Pino from Dynamis with Carlos Aramburu. We'll be talking about calcined clay technologies. We have Tony Hadley from his African advisory consultancy, who will be talking about the commercial case, the economic case for using calcined clays. But first, our first speakers and a very practical case study will be given by Simpor Global Holdings and OYAK, and I'm particularly pleased to be able to introduce them now. If I could ask Berkan to start sharing his presentation slide deck, I'll make the introduction. With us, we're delighted to welcome the chairman of Simpor Global Holdings since 2018, Mr. Suat Chalbiik, serving many industrial enterprises in the fields of cement, steel, energy production and distribution, natural gas distribution, food, industry and construction, and having 36 years of sectoral experience, which includes the ownership of various engineering companies. Mr. Chalbiik has been president of OYAK Cement Concrete Paper Group since 2016, and as I said, chairman of Simpor Global Holdings since 2018. Welcome, Mr. Chalbiik.
Thank you, Mr. Thomas. Good afternoon, everybody. You say the 36 years experience. You explained my age.
You don't look a day older than 36.
Thank you. During the face-to-face meetings, I have the dinner for you.
Thank you very much.
Thank you for everybody. I hope that this presentation gave the explanation about calcined clay. We named them the OHH clay. Simpor Holding is established 3 years ago, but do you know that the Simpor is in Portugal and Turkey? The owner of the Simpor Holding is the OYAK, is the biggest pension fund in Turkey, and the other partner shareholder is the TCC, Taiwan Cement Company, in biggest producer in China, 6th biggest producers. Do you know that in cement produced in all the world 4.1 billion ton, is 2.1 billion ton produced in China, and our partner is TCC, Taiwan Cement Company, is approximately 85 million ton annual production capacity in China and Taiwan. Also, Simpor Holding reached the capacity 32.6 million ton, rest of the world, exception China. Totally 120 million ton cement production lines. These two biggest group aimed and target is decreasing the CO2 emissions in all the world, because maybe a few days ago, one meeting discussed again the next big problem in the human life is the CO2 emissions and climate change. Therefore, our two groups have the research and developments about this issue. Simpor is approximately allocated 5% budget of the annual for the research and development group. This is one of them, our developments and improvements of the project. Simpor Holdings also have the experience calcined clay and the know-how about this project. And we can explain our Simpor target is 5S. What is the meaning of the 5S? One is sensitive to environment. Second is sensitive to human life. Third is sensitive to local traditions. Fourth one is the sensitive to universal rules. And last one, sustainable business. Our target is always, is approximately, if we end of this year or beginning of the next year, we can introduce the low carbon cement in approximately reduction to CO2 92%. This is the big target we can reach to the end of this year. Now, Berkan explains the details and our research and developments about this project. This is one of them. You can see that the near future, our other project about cementitious materials. Thank you again, Thomas.
Thank you very much, Mr. Çalbayık. That's a very good introduction to the group. And like you say, the combination between TCC and Oyak and Simple Global Holdings. And now a quick introduction is Berkan Fidan will continue the presentation. Berkan has worked in the cement industry for 14 years. His career began at Denizli Cement Plant in 2007. In 2008, he became Performance and Program Manager at Oyak Cement, and since February 2019, he has held the position of Performance and Process Director of Oyak Cement Group. Please, over to you, Berkan.
Thank you, Thomas. Thanks again. Firstly, I want to say welcome to all the participants and also for that organization to Semtech. Thanks for Semtech about that. As Mr. Chairman explained that, it's our topic, and today is about our calcined clay technology, and we named it as DOH clay technology. And our projects, we have an ongoing project in Cameroon, also a completed commission project in Abidjan. I will try to explain our experiences. The cementitious materials, I want to start with just short, brief introductory about that, the CO2 issues and other things. As we all know that the cement is the largest manufactured product on the earth, and the second most used substance is the concrete, which is produced from the cement. And the total of cementitious materials make up nearly 50% of everything we produce, and also it's responsible from the total anthropogenic carbon dioxide emissions, nearly 10% of that emissions. There's a roadmap. It's many roadmaps available to just decrease the CO2 emissions. It's one of the most important topics. Also, not these days. It's a story just, but it becomes much more critical due to increasing temperatures of Earth. But at the meantime, also populations increase, and global cement production is set to grow up more than 23% according to high variability case, and in low variability case, it's around 15% by 2050. Direct CO2 emissions is also expected to be increased in 4% in globally. And when you look on the trend, expected trend from to the 2050, it seems like it's today's one of our topic is Africa, because we just focused on that continent. And when we look on it, the Africa, it's nearly triple than today's value in 2050. Also, as we discussed from one of the agencies, that International Energy Agency just shared that plan and the program about that, its current situation. I used their data about in here, and according to our reference technology scenario, as we need to reach the 2 degrees Celsius scenario. There's a difference between that issues, because our reference technologies are not enough to do that decrease the CO2 emissions to reach the 2 degrees Celsius target up to 2050. When we look on it, there need to be a 7.7 gigatons carbon dioxide need to be reduced till the 2050 But when we look on how could we do it as a cement industry on our side, just there are four main topics. It's just coming, the most effective ones. In the first stage, it becomes also popular and it's very critical. The carbon capture and oxy-fuels issue. The innovative technologies are also critical. And it's a just started journey, and many projects and many research activities are going on, but there need to be some time to get the just expand the results and just input into the industry. On the second stage is the reduction of clinker to cement ratio. It's also known issue, but because of that, it's also known just blended cements and other issues. Also, cement industry try to decrease the clinker contents of it, but there are some drawbacks at near future. And we focused on that issue mainly to, besides that fuel switching, thermal energy efficiency and other electricity energy efficiency, we are doing also investments and other things. But we believe that in short term, the most critical action is to quickly decrease the clinker ratio to just decrease the CO2 emissions. When we look on it, CO2 emission, supplementary cementitious materials are critical on the decreasing clinker ratio action because something needs to be replaced with clinker. When we look on the availability of that materials on the world, it's just there are some tiny amounts and specific materials like rice husk ash, silica fume, and burnt shale available. Also, there are natural sources, but it's not spread all over the world. In Turkey, we are a little bit lucky about it, but all around the world, it's very limited amount of natural pozzolans available, and they are also limited reserves. Depleted and will not be available in some day if we will consume it like that. On the other side, the most used ones are blast furnace slag, and fly ash, and also steel slag. But at the meantime, that 2 degrees Celsius scenario, it's based on also some actions on that steel industry and also energy production, energy industries. And that also starts in Europe, that plant starts to close and recycling becomes much more active, and new energy, green energy sources also starts attractive, and that amount of that material will become much more less. At that point, the only point is limestone as a filler component. It's left. Yes, there are many available reserves like that for limestone all over the world, but the problem is that its reactivity, it's not a pozzolanic material. It helps some reactions on the early strengths and other things, but high quality cements, high strength cements could not be easy to done with the high amount of limestone added. At that point, the choice, it becomes the potential choice, it looks like on clays, and we focused on that point. When we look on the clay option, it's just thermally activated clay technology also becomes much more popular. It's also just, it seems like, and just assumed by EIA again, its reports in 2018. It's, as you've seen, it's around still, besides the fillers, the reactive, high reactivity pozzolanic materials like that, blast furnace slag is the first leading one. But when we look on the 2050, according to scenario of 2 degrees Celsius scenario, it's the most, the high reactive pozzolanic materials leading one becomes calcined clay. It was from 0 to 8%. It's a huge amount in the of cements. It will directly affect that CO2 emission reductions. What's the concept of thermally activated calcined clays? It's just clays. It's a very known and very abundant material in all over the world, and there's some specific metallurgical compositions available. It's just the most known ones are just 1-to-1 and 2-to-1 compositions, but when we look on the reactivity after thermal processing, its most reactive ones, kaolinite, and also after that, illite and montmorillonite is also reactive materials. But kaolinite differs from the other clay minerals due to its 1-to-1 composition. That one-to-one composition is based on the oxygen silicon tetrahedral sheet and octahedral sheet with a single octahedral sheet, oxygen hydroxyl group with alumina. And the process is based on with the thermal process, as you could see in the bottom part for kaolinite. It starts more after 500, 550 degree, it's a delamination, and then dehydroxylation starts. And after that, the formation of metakaolinite. Metakaolinite is a known product, and it's also with high purity of kaolinite. Many industries also using it. But in calcined clay issue, the aim is to use just not a specific clays, just to find it achievable and proper clays with mixing kaolinite, illite composites and other things with some specific features to get really reactive supplementary cementitious material. On that point, just some also photos from our, exactly from the photographs from the fields and our, while we are researching clay for Abidjan plant in Ivory Coast. It's just in Africa, it's also available, especially in West Africa, abundant resources available over that bedrock, high thickness of material available for clays. When we look on that, it's for calcined clay production. One of the other reason of kaolinite's one-to-one formation, the other issue is about the thermal processing, the hydroxylation range. As we could see from the graph in the graph in the left part, as you could see that the kaolinite has the highest range of that dehydroxylation temperature starts at earlier after 550, and then it's after 950 there is also an exothermic reaction starts and the crystallization happens when also the realized crystals like mullite and cristobalite, which were also new crystal formations, and they are not reacting. And the aim is to keep the process between that margin, it's red dotted part, to reach highest dehydroxylation temperature, dehydroxylation process, and also to keep the products non-crystallized. By that way, it's highly reactive compositions can be achieved. And the second part is illite can be used, as you could see in here. Montmilonite is also can be used, but the disadvantage of montmilonite is the hydroxylation range between the endothermic and exothermic zone, the hydroxylation part and then the recrystallization part. The temperature range is very narrow, and it's not easy to control it. If high amount of montmilonite materials available, then there's a risk to cause recrystallization or non-dehydroxylated part. Because of that, we focused on firstly on kaolinite and then illite compositions on the reserve just surveys. When we look on the quality, it's just, as we said, as you can see, it's different type of clays from just taken from the field. It's different colors, different composition and physical characteristics available, especially quartz introductions are very high with that type of material. The process is based on screening, crushing, and mixing together homogeneous formation of raw clay and then prepared feeding, dried and dehydroxylated, and then there is a final product taken out. It's just there's a range according to composition and mineral formations. It's between 650, 700 degrees up to 900 degrees. It's related, as I explained. It's based. It's a tailor-made issue, the process design and the receipt. It's related about the raw material. When we look on, it's our first product, a photograph from our first product, when just at the mid of August, we produced industrial first product. You see the DOH clay, it's color issue, and when added the cement, its effect. By the control of reducing atmosphere, it became much more darker. We could achieve it. And when we look on the quality detail, it's just, as I explained, the most important part is just differential thermogrametric, and also at the meantime, besides the thermal gravimetry, also scanning calorimetry. You could detect where the hydroxylation happens, where crystallization can start, and where the other impurities dehydroxylated. It's easy to define it. The kaolinite has an advantage that easily distinguished according to amount of heat. The heat for the endothermic heat formation happened, and also the mass loss. It can be detected the amount of kaolinite by the help of that analysis. And based on that issue, we just create a receipt on our studies, and according to quarry formations, we try to keep the zone and select the samples, and then do the survey and just design the mining requirements. The question is now, it's why did we start with West Africa? It's just, I just want to explain here, CO2 emissions must be decreased, need to be decreased all over the world. Yes, Europe is much more active. China is really just doing many things about it, but also we are using the same atmosphere, and it's also critical to decrease CO2 emissions. One reason is this. The other most important reason is that when we look on the geological formation of Africa, in the right side, you could see that it's a calcium carbonate contents in here. And the West Africa, especially sub-Saharan region, it's very low content of calcium carbonates. Generally, northern part, the calcium carbonate reserves. And due to that reason, as you could see in the left part, in the left, the red zones, it's yes, there are some clinker producers available, but mainly the clinker just imported by them. And at the meantime, also cement getting imported to Africa. It just when we just look on that opportunity, it's just there is also CO2 not only due to production cases, also shipment and delivery. Huge amounts of clinker is coming, and it's also an effect on the CO2 basis indirectly. And the second, it's when we look to kaolinite availability, especially kaolinite and clay formations, we could see that it's the world map. In left part is topsoil and the right part is subsoil zones. As you could see in the light blue and the yellow one is the kaolinite, light blue is illite formations, are generally favorable to do calcined clay, and that thermal activation of clay, you could get reactive materials. As you could see that it's just in the West Africa, both in topsoil and subsoil, it's very proper to produce its own cementitious material rather than getting all the clinker and also supplementary materials away. And also just specifically when we look on the sub-Saharan region, also there are nearly 30 soil types available in the soil literature. And when we look on it, it's the 5 of them, it's critical according to their alumina and iron contents and also the other compositions. The soils generally favorable to include just kaolinite and proper kaolinite contents in it. When we look on it in the right side, it's just that soils can be seen, and their availability also given specifically under their visual. And you could see that it's just in the West Africa part, it's really has a great potential about that materials, and also for producing calcined clay. Now I want to just talk about a little bit the production technologies, about rotary kiln and flash calciner technology. Everyone just comparing them and just giving some idea about it. We just preferred rotary kiln and dryer option in our first plant in Abidjan, and the second plant will be commissioned in Cameroon, and it will be a flash calciner design. Our aim is to experience both of them, because we believe that there is not an exact decision. It's late about the conditions, material issues, and other details. And also we want to experience both of them because we believe that calcined clay will be much more important, and we have to get some experience from both technologies. On rotary kiln and rotary dryer and kiln option, just experience. It's just nearly more than 6 months, nearly 6 months passed after first operation, and we have some experiences on it. Just to give some roughly about that, some details. For the advantage part, it's a simple design, as we all know that, and it's a well-known process. And the feed material is not so fine like flash calciner option. It should be wide range of feed size, and it's just can be acceptable some coarse portions. And moisture content, it's much more flexible when compared to flash calciner. No need to dry it. It's a coupled design, and dryer is also coupled with the pyro zone, the combustion, the dehydroxylation zone. That's the advantage on flexibility on moisture content. And also potential of increasing efficiency and capacity according to moisture content. If less moisture, it's related about the kiln design, but you could get higher capacity and less energy consumption can be done. On the other side, it's drawbacks. It's a little bit lower sensitivity on process control because you could not check inside of the kiln meter by meter, and you could not control it. You just get the output material, especially if the feeding material is not so homogeneous and both in moisture and mineralogical formation. It causes deviations on the final product. And color control is another issue because a direct flame is used in rotary kiln, and reducing atmosphere, creating a reducing atmosphere, it's a little bit complicated when compared to other options. And because of the bed of material flowing bed, it's thermal effect over particles, it's not even, and that causes some particles maybe crystallized, the other ones not exactly dehydroxylated. It's an issue for rotary kiln. And secondary requirement for debate about direct flame, and fuel's flexibility is a little bit limited when compared, because indirect gases, it's the flame is controlling the process, can be adaptable, but when compared with the other solution, it's a little bit complicated. And also, if the heat process cannot be controlled well, some agglomeration, ring formation risks, and they may cause also process faults and failures of the system. On the other side, it's the flash calciner option. We will just commission it in the end of this year, late at the beginning of next year. And according to our investigations and pilot scale applications with the technology partner, we observed some advantages and also some disadvantages. It's basically flexibility on process control. You could control in each stage of that pilot process. You could increase oxygen content or create reducing atmosphere. And heat transfer is much more effective when compared to rotary kiln because fine ground material and just heat transfer efficiency is higher when compared to kiln, rotary kiln. There should be various, there's a various fuel options available, just secondary fuels and any other thing. Recirculating the gas can be used, and it creates also flexibility on that part. And heat recuperation is also efficient. And also easy to operate with reducing conditions because it can be managed. The reducing atmosphere can be oxidized in top stage or some other place then without any danger or risk of that just in the process. And also limited rotating parts and maintenance requirements when compared with the rotating rotary kiln and dryer option. On the other side, there should be a fine and dry feed size required, and there must be a pre-drying and pre-crushing heat to be applied. It could be applied in a coupled design with specific and other equipment. And also the material transferred with air, it causes a larger system fan rather than only ventilation. It just drops the material top, and it creates also working airs with high dP, and it creates more electrical energy consumption on that specific issue. But also there is also the other advantage, as I explained. The other thing is also vertical construction and civil works. There's a tower that's around 50-60 meter height according to capacity requirements. On the other side, rotary kiln, it's no need to just create. You don't want to do a construction like that. Now I want to introduce our first certificated DOH clay blend cements in Africa. Two types of products we just served in the market, and these are CEM2AM QL 42.5 and SEM4BQ 32.5. It's the backs of it, and the certificates, it's first taken certificates in Africa. When we look on the quality of that first results and we have got achieved, it's when we just compared it with SEM2 42.5 and the existing one other product is SEM2AI. The other 42.5 product, new product is SEM2DM, which including calcined clay. As you could see from here, it's just in the early strengths, it's just a little bit down on it, but in the late strength, it achieved more than SEM2AL and just a little bit higher than the SEM1 42.5. It also gives us a opportunity to check and to improve it, to increase the amount of calcined clay. When we look on the reduction with CO2 reduction issue with DOH clay, DOH clay, when compared with the OPC, you could see from the graph at the bottom and the left part, the OPC clinker, standard OPC clinker. Blue columns are the heat consumption to produce that product. And the gray ones are the CO2 emissions while producing that product. And also the orange trend that shows the electricity consumption while producing per ton of that product. As you could see that it's while producing OPC clinker, it's around, when compared with the DOH clay comparison, it's nearly 23% less heat consumption used to produce 1 ton of DOH clay. And the other option in the right side is the low carbon option. We are planning to produce that product at the end of this year. It's based on some adaptations on the fuel combustion and also using secondary fuels and the other options, especially the just using rather than fossil ones, it's just using some biological biomass compositions. And if there is also some difference on it about heat consumption, a tiny difference, but it's also 19% lower than the heat consumption of OPC clinker. When we look on the CO2 emissions part, there's a drastic drop when we with DOH clay. Per ton of when compared to per ton of OPC clinker, per ton of DOH clay emissions is 65% less than OPC producing 1 ton of clinker. And with the adaptation of that secondary fuels, due to the only source of that CO2 while producing DOH clays comes from combustion part, not the in-process raw material part, because there is not any calcination, decarbonation. It's just related about dehydroxylation, hydroxyls, water vapor is removed, and it helps to decrease it if the heat energy can be supplied from less CO2 emission, including materials, fuels, then there's a chance to more than 90% decrease. And while producing cements, also additionally, specific electricity consumption when compared to OPC clinker is nearly 65% less electricity consumption required while producing DOH clay. When we look on the CO2 footprints, as you could see, the DOH clay blended cements are existing production in Abidjan plant when compared to SEM1 and the other mid-blended and high-blended products. Our aim, as I explained the previous slides, the low CO2, low carbon DOH clay, we are planning to use it, and also additionally, our advantage to use additional some supplementary cementitious materials, and we just checked it, and we could achieve less than 200 kilogram CO2 per ton of cement. It will be a specific product, as our chairman explained that. We are planning to introduce it to market end of this year or just beginning of next year. It's a specific product, that cement. Yes, the first plant with the DOH clay production line in Africa. It's just we commissioned the line in August 2020 at Abidjan plant. You could see that the visual of that plant, the project visual. It's up to 3,000 ton per year DOH clay production capacity and 2,400 ton per day cement grinding capacity of the plant. As you could see, it's in the middle of the plant. There is a stockhole on it, and just there's a line, and behind the stockhole, it's just the feeder, clay preparation, kiln feeding, rotary dryer, and cooler units. And the other side, at the back of the stockhole, cement grinding unit. It's a compact plant. And the first figures, as I said, on the right side, it's 16th of August, the first day of commissioning. It's the first product, the first DOH clay. It's just in the Africa, just in our hands, and at that date. And just the first figures, it's related about the raw clay properties. We are just trying to opportunities and mixings on it, but roughly we can say that it's between 557 kcal between according to moisture content and the kaolinite and illite compositions required the hydroxylation rate, alloy contents. It's related about it. And for the energy consumption, again, it's related about how much produced and mineralogical composition and other issues of that material. It's between 18 to 23 kilowatt hours per ton to produce 1 ton of calcined clay. What are achievements? We saw that it's just the grinding stage and blending adaptations are much more complicated than the thermal processing stage. Everyone talking about comparing just producing calcination process and other things, but the product is a unique for each plant and should be studied well and just investigated well to produce materials. I will explain in the next slides about the short info about it. And cooling stage is also critical. Its material is dusty and it should be just selected properly. The cooling is also critical and directly affects color, heat consumption rates, and the burning efficiency. As I said, there's not a typical design. It should be just investigated well with the plant requirements from raw material to products. And just I show a variable cost difference to show it. It's heat energy is one of the most important factor. If you could solve it with, if you could find some alternatives on it, also you could drastically decrease your variable costs. Just some operational criteria I want to say it is the quarry and survey is critical. As I said, we did studies with our partners on it. As you see the photos in here, we just checked several reserves, several zones to found the correct reserves. Mineralogy part is also critical. There should be a balanced silicium and aluminum oxide contents and mineralogical compositions. It should be checked well. There's just a sample of our study, exact study on it. As you see, it's just kaolinite and illite contents. You should have to get as much as possible amorphous content to get the highest reactivity with the optimum process conditions. After a higher temperature, as you know that one side it goes to crystals with non-reactive and hardly ground mullite, cristobalite, and other things. The other part is non-dehydroxylated portion. It causes also quality problems on the cement side. Clay preparation is also critical. There need to be simple, robust units. Pyro process need to be well managed, and stable combustion and heat optimization is critical to decrease the variable cost and emissions and everything. It should be done. Quality, it's just important. Online monitoring is also critical. As all we know that we are just managing kilns with free lime content and sampling on it, and that there should be something decided on the quality of producing calcined clay. It should be color. It must be color. It must be just the hydroxylation rate control with the specific equipments. We also managed and we just produced our own quality control formation and procedures. Color, as I said, is critical and related with the reducing atmosphere. Dedusting and filtration important because we are talking about very high moisture contents and very high amount of water vapor. The filtration systems need to be selected according to that one. Cooler design is critical because not only the cooling effect, also recuperation and heat efficiency is directly affected with that one. Additionally, also oxidizing and reducing atmosphere also related with the cooler. It's also critical to do it. And then just I said, the grinding stage is critical because it's not that standard supplementary cementitious material like fly ash or steel slag or blast furnace slag. We are talking about the raw clay and just removing its moisture, and it's late about the clay composition. I just want to just show some figures in here, just exact figures we show in the plants from different countries in West Africa we investigated. I just mixed and summarized some of them. As you could see that it's just Blaine residue. In the left side, you could see the D10, D50, and D90 micron figures in here. In the right side, you could see that the Blaine fineness and the residue. It's known in cement industry, but it's not related about it. It's just some of the portions just pulverize very easily and goes more than 9,000, 10,000 Blaines over of it. But the other portions left coarse, and it directly affects co-grinding, separate grinding selection. It should be investigated well. That part is critical because it directly affects the concrete rheology and water demand and other stages on the concrete side. We have been working also on it since last 6 months. And lastly, I want to also introduce our first greenfield DOH line with flash calciner. It will be the first. It will be the first plant in the world with flash calcining, and it will be again in Africa, in the Kribi, Cameroon. And the design capacity is again 720 ton per day thermal clay activation and 2,400 ton per day cement production capacity. We just checked it. It's with our technology supplier and just doing tests on pilot scale with the small units with exactly samples, raw materials from Kribi. And also the construction is going on now in Kribi. And we are looking for that opportunity. As you could see the layout of that plan and that plant's general layout on the right side. Thank you again for just listening. We are ready to answer your questions if available. Before that, we have a short video about I need your help about Thomas to just.
Yeah. Okay, so I'm going to ask you to take your presentation down. I'm going to share. Hopefully you will be able to see this video. And there we are. That's a fantastic presentation. Thank you very much, Berkan, for that very clear description of these fantastic projects in West Africa. They are pioneering projects. We think they have a great future and that this is probably just the beginning. I was just wondering, just from a practical sense, now that you're entering the market, people have always said that these markets are very conventional. They only like grey cement. They don't like changes to the products. What is it in practice? How has it been accepted by the market? And also, can you talk a little bit about the regulatory structure and standards, and has that been something of a challenge in order to launch the product?
Yeah. Just about regulations, as you said, it's a certificate product in EN standards. It creates some complicated situation because calcined clay, the LC3, known amount as 35% calcined clay, 15% limestone, could it be possible with existing EN standards under the 97? Because of that, we have to fit our product according to that product type, SEM2A BQL as I explained, and the SEM4B Q. But in the market, we just really get positive feedbacks about our products, and just introduced in the market. But our aim is to just explain the people about that product. Yes, there are some specific issues need to be controlled. We are doing many R&D on it and studies on it to just arrange its water demand and other thing and quality properties. We try to keep it same as the other products. But at the meantime, it's also a positive effect. It includes more than the others in the African material. It's just the clay of Africa, we are saying, and we hope it will be much more higher in the proportion. It goes up.
Sure, and it's a remarkable solution to the issue of the lack of limestone in West Africa, and you're able to avoid the clinker imports. And we'll be talking more with Tony Hadley on the economics of the rationale for these kind of projects. But if I could ask Mr. Çalbayık, this is quite an advanced pioneering vision for West Africa. I was wondering if this is something that was conceived after the Simpor Global Holdings tie-up with TCC in China, or has this been long planned, this initiative?
Thank you, Thomas. And the TCC is the Taiwan origin company. First one, I want to correct that, is that we have the more issues about the Africa continent. Till now, do you know, Africa local sources uses other continents. But this product used in local countries usage for the improving the local sources. Therefore, our aim is to reach the 5 different countries. The OH clay in the Africa, we are continue the investment in the African countries. We can believe and we can trust the African people.
It obviously has huge potential in Africa, and as Berkan pointed out, the local clays are abundant. Yeah. Do you see a lot of opportunity in other markets, for example, Turkey, or over in Taiwan and China? What's the kind of global potential in your mind for this product?
Do you know the Simpor Holding and the TCC and OYAK group have the footprint in all the continents? For example, the OYAK is 19 country, is 92 company in these countries. In Europe, first one, we can make some research about Europe. China is the good opportunity about that. You can see Berkan presentation also in the Russian and Ukraine area, also in the America have the good potential. This is near future. The cement sector and the investors recognize that this component very well. Why? We must find the solution to decrease the CO2. This is the big opportunity. In Europe, do you know the big opportunity for the CO2 emissions? Starting to the new phase 2023 till the 2030. And our Simpor Holding aim in Europe, decreasing the CO2 emission 30%. We can explain this our target in all our sharing on our customers. This is our aim and our task for decreasing the CO2 emissions. Do you know that the cement sector also second big producer to the CO2 emissions? We must find the solution hand by hand. Therefore, we sharing our experience with our producers, and we we are every time make some opportunity together for improving the most effective cementitious materials. Also, OYAK, producer of the slag, is annually 3 million ton produced the slag. Also, we can use in Turkey that cementitious materials. And our next step aim is Europe, China, and America. We can implement this project. In Africa, we are continuing in Africa, reach to the 5 countries, different countries.
Well, it's clear that the potential is enormous, and as you mentioned, the whole sustainability agenda has now become critical, and we've seen that in our conference in September, our decarbonisation conference. Many companies are speaking about the net zero targets and reducing substantially their CO2 footprint in the next 5 years. And it looks like OYAK and Cimpor are going to be at the front line of that process, innovating and pushing these technologies into the market rapidly on a global basis. So we really have to thank you very much for joining us today. We could talk in great detail, but I know we have to get on with the schedule. But I do hope you'll come back and report on the next project with the flash calciner. I know that's a new technology, and the world is watching to see how that will be. So good luck. Thank you for participating today.
Thank you, Thomas. Thanks a lot.